Welcome to this explainer. You probably filled up your water bottle on campus today, or maybe made a pot of coffee in your dorm without really giving it a second thought. But today, we're going to take a calm, fascinating look at the essential and highly engineered journey of how raw, untreated water from rivers and lakes is actually transformed into the clean drinking water we all rely on every single day.
I want to start us off with this really grounding quote from the source material. It says, "In many ways, water is a miracle liquid. It is essential for all living things on this planet." And it really is, isn't it? As an engineering material, water is arguably the absolute most vital resource we have. But here's the catch. The water we pull straight from nature just isn't automatically ready for us to consume. It carries biological impurities, dissolved minerals, and all sorts of suspended particles. So, to unlock this miracle liquid for human use, we have to guide it through a very deliberate, careful process.
Section 1. Defining the destination and specifications of potable water.
Okay, so before we figure out exactly how to clean the water, we need to understand our end goal. And the absolute crucial concept here is potable water. Now, this isn't just a fancy scientific word for tap water. Potable water is a really strict standard. It's defined as drinking water that is safe enough to be consumed by humans or used with low risk of immediate or long-term harm. Basically, it's an engineered state of water that has been meticulously stripped of its natural, harmful impurities.
So, what does that standard actually look like when we break it down into chemistry terms? Well, it's a really interesting mix of sensory language and exact scientific parameters. The water must be sparkling clear, perfectly cool, and entirely odorless. But behind what we can sense, there are some very strict rules. The pH needs to be perfectly balanced, right between 7.0 and 8.5. Turbidity, which is basically just a term for cloudiness, must be less than 10 parts per million. Total dissolved solids have to be under 500 parts per million, and of course there can be absolutely no heavy metals like lead or arsenic, or objectionable gases like hydrogen sulfide. That's the one that causes that awful rotten egg smell.
All right, so here is the roadmap for a typical water treatment plant. We start with screening, then move through aeration, coagulation, and flocculation, sedimentation, filtration, and finally disinfection. Let's just walk through this entire process step by step, starting right at the very beginning at the intake.
Section 2. First steps. Catching debris and breathing. This is the very first phase of the physical treatment process. Step 1 is screening. Just imagine a massive industrial version of the filter in your coffee maker. Raw water is pumped in from a river or a lake and immediately passed through coarse and fine screens. This acts as our first line of defense. It captures all the large floating debris. Think leaves, twigs, rags, and plastic. We absolutely have to do this right off the bat to protect the main units of the treatment plant and to stop these large objects from completely destroying the delicate equipment further down the line.
Right after screening, we move into aeration. And I actually love this step because it's just so elegant. The water is gently cascaded over a series of steps, completely exposing it to the open air. It's literally taking in oxygen. This added oxygen helps naturally expel soluble, acidic gases like carbon dioxide and hydrogen sulfide. And getting rid of those gases is a game changer because it makes the water less corrosive and removes those bad tastes. Plus, the extra oxygen reacts with dissolved iron and manganese, turning them into solid, insoluble particles that we can easily just catch and remove later.
Section 3. Settling the invisible impurities.
So we've successfully removed the large debris and the bad gases, but the water is still cloudy. It's full of these microscopic, suspended particles that are just way too small and light to sink on their own. This is where the real magic of coagulation and flocculation comes in. You see, these tiny suspended particles often have negative electrical charges, which means they actually repel each other and just stay floating around. To fix this, we add a positively charged chemical called a coagulant to neutralize them. Then, the water flows into a flocculation basin where it's gently stirred by these big paddles. It's kind of like gently gathering microscopic dust bunnies on a hardwood floor. As the particles bump into each other, they stick together, forming much larger clumps that we call flocs. And the really clever part? The mixing speeds intentionally decrease as the water moves through the basin. We slow down the stirring so those newly formed, super fragile flocs don't just break apart again. Now that we've engineered these large, heavy flocs, we can literally just let gravity take over. In the sedimentation phase, the water flows into these massive, quiet settling tanks and just sits there, completely undisturbed, for about 2 to 8 hours. Slowly and peacefully, the heavy flocs fall to the floor of the tank, forming a layer of sludge that gets removed later. This incredibly gentle, passive process actually removes about 70 to 75% of the suspended impurities.
Section 4. The final filtration.
But as you can probably guess, 75% clean definitely isn't 100% clean. So the water moves into a rapid gravity filter, where it gently percolates down through deep beds of extremely fine sand and coarse gravel. As the water weaves its way through the tiny, microscopic spaces between the sand grains, any remaining fine particles, remaining color, and even trace odors get trapped. It's essentially nature's own purification method just scaled way up for an entire city. And the water that emerges from the bottom of this filter, it is visually crystal clear.
Section 5. Disinfection and delivery. But here's the thing. Crystal clear does not automatically mean safe. Even after that incredibly thorough filtration process, a tiny percentage of disease-producing bacteria, viruses, and pathogens can still slip through. If we drank it right now, we'd be risking terrible diseases like cholera or typhoid. So disinfection is absolutely crucial. It completely destroys these remaining biological threats. But just as importantly, it provides a residual layer of protection. It ensures that as the water travels through miles and miles of dark municipal pipes to get to your dorm or apartment, absolutely no new bacteria can grow in it.
The most common and, frankly, most effective way we do this is through chlorination. And the chemistry here is wonderfully direct. When chlorine gas is mixed with water, a chemical reaction takes place that produces something called hypochlorous acid, or HOCl. This acid is a highly active, powerful germicide. It literally penetrates the cell walls of the bacteria and completely neutralizes them.
But, and this is a really big but, we have to be incredibly precise with the math here. Which brings us to a fascinating concept called breakpoint chlorination. Think about it. If you add too little chlorine, the bacteria survive. If you add too much, the water tastes like a public swimming pool and can actually be irritating. The breakpoint is the exact chemical sweet spot. It is the precise amount of chlorine required to completely oxidize any remaining organic matter, destroy all the ammonia, and eliminate bad odors, leaving behind only a tiny, safe, free residual of chlorine. And that free residual is basically a protective shield for the water all the way from the treatment plant right to your glass, ensuring perfect safety without an overwhelming chemical taste.
So from raw, cloudy river water catching leaves in a screen, to breathing in oxygen over a cascade, to gathering tiny particles into flocs, settling, filtering through fine sand, and finally being perfectly balanced with exact chemistry to keep you entirely safe. It really is a true engineering marvel. Next time you turn on the tap to fill your glass or water bottle with that cool, sparkling liquid, will you think about the incredible journey your water just took? Thank you so much for joining me on this explainer, and I'll catch you on the next one.